Everybody, welcome to the Mankind in Training uh, Wolfram Quantum Framework Study Group. It's the first one. It's our first live one anyway. Um, I would like to do something a little different. I've been rambling through everything that Wolfram can do, which is quite a lot. It's an absolutely stunning computational tool, but aside from all the things that Wolfram can do, I there are some implications for like what is possible anyway. There I've been playing with this for some time now, and I've discovered that now anybody can do a form of research, and here's the reason why. The fact that we can create these states that we couldn't possibly see in nature, and then we have these analog named states that we know what they look like. So we can do operations where we apply these fictitious states that you can build. Like, you can make anything into a state. It's very versatile, actually. Some things will trip it up, but you'll usually find that it's you're doing something wrong. You're calling something incorrectly, or like uh that is a thing, but it needs parameters. There's bits and pieces of. So I want to break this down a little bit. What's going on? So the best way to do that, in my opinion, has always been to go look at like the documentation, and you can see the documentation for Wolfram is absolutely amazing. Just the scope. So like literally everything can be built in terms of a quantum basis, a quantum state, or a quantum operator of some kind. Or uh if there's enough different things, it needs to be a quantum circuit operator. This is the repository, Wolfram Language Packet repository. This is a block sphere. This is a quantum circuit down here. It looks like a is that a Grover amplification or something? A measure on one, a measure on two, and a measure on three. A C0 gate, and then like a controlled. I'm not sure what the distinction is for when it's not filled in. You have to look at this is a multi-way kind of diagram. Um, but yeah, I was unpacking. Okay, so the state, anything can be made up in terms of states, bases, operators, and then you can build states and operators and measurements up with tensor products. You can do partial traces, and everything is in the documentation. So this is like the basis A and B with amplitudes of 1 and I and 2 and negative I. It builds up quantum basis that is a Schrodinger matrix. They're all kind of can be built into matrix representations, and then you can. It's crazy. Wolfram's so sweet. You do any kind of math at all, and usually it says underneath of it, would you like to turn this into a plot or a matrix or this or that? It just asks. You don't even have to type stuff. You can just click it. I love Wolfram. It's awesome. I'm really glad that I finally hawked up. Like everybody kind of talks smack about it, but it's just because they didn't bother to pay for it. If they paid for it, they'd like it. Because it does everything. It does everything for you. It has some limitations, but they're fixing them. So like these quantum states and these quantum bases, we can do a customization like this, where this has 4 different amplitudes that they designated in a quantum state, and it made this colorful looking array map of the matrix of what that looks like. And then those were the amplitudes for it. I like that. This is a 0, 0, 1 quantum state, and it knows exactly what you're trying to do. You can use the convention like that. But if you're trying to specify you want a 0 state, comma, you want a 0 state, comma, you want a 1 state, that's basically the same thing. It's just shortening it up. But you can build, back to what I was getting at, you can do research. Anything you can dream now. You can look how a state that is a faux state that we create on this framework and see how it behaves with once you apply a different state to that basis, or once you turn it into an operator of some kind. You can turn I um I'm so impressed at what you can actually do. You can turn everything into anything. You can designate a quantum state like this if you prefer, because like most everybody used to seeing something that looks like this as a representation. That creates I think a Bell state kind of looks a little something like that. And it's such a powerful computational tool in the sense that you can make these states and it does all the math then for you. You don't have to do anything anymore. You can ask it for all of the properties of a state. If you know what to designate, like up here, here, create a superposition of 3 qubits, 2, 3, which is exactly what this is. And it's made the state. And then let me, they made it too easy. Back in the day, we had to type everything. Now you can just, all these notebooks are all interactive, all the documentation's interactive. It's so cool, man. So sweet. Ooh. But anyway, back to it. So you know what we want to designate. We can do it. We create the state. So say uh the implications for what you can do in the sense of investigating building a molecule of some kind, like a custom element that is heavy, say. We can see how that behaves. The documentation though is just so very, and then when you get to the bottom, you're not at the bottom. Don't worry. Keep clicking on these things. There's more. There's always more and more and more and more and more. Who's I want to just make sure I give props because on most every bit of all of the documentation I've read. Ah! Why does that happen? Um, I was trying to give Jonathan props because I see his name all the time, but I don't see it now. I don't know how to pronounce your last name. I'm sorry. But I believe he's wrote a lot of this documentation and it's very impressive. It's thorough most of the time. Have I been disconnected? I've not been disconnected. Huh. Sorry, I should be talking. So I I mean other than to state the fact that the implications for doing just about anything. So uh Wolfram's even good for doing like evolution time systems. So I seen a demonstration where the gravity was being demonstrated, or how ER equals EPR literally came out of uh, a, a simulation that was done. And what that is saying is so ER versus EPR. If that is like an emergent property that you see after however many time steps after looking at a black hole or whatever it was that showed that this emerged, ER versus EPR is saying that don't worry about a wormhole collapsing your house because it's fine. Wormholes happen all the time, and that's actually how spooky action at a distance is occurring. Is that they're literally they they kind of are folding space and time all the time. the particles anyway. Energy at scales that small. Uh, the Einstein-Rosen bridge, the wormhole, is stabilized naturally by particles. The electrons are doing it. ER it equals EPR. So we can technically, in theory, stabilize a wormhole by sending a negative charge through it. It's either a negative or a positive. I can't remember which one it is. It's one or the other, though. And it would stabilize the wormhole simultaneously for something to get through. But I suspect that the bound for what's like the size of something, a mass m that could go through a wormhole that has been stabilized artificially is probably, I suspect that it's very small. We're not going to be sending anybody through any wormholes anytime soon. But I found uh there is an article, somebody has made a wormhole with a quantum computer. They simulated uh moving a qubit out of position, if you will, in a circuit. They took a qubit and had it in one side and moved it to the other side, and it wasn't possible. They trapped it and moved it with entanglement. Oh, yeah, duh. Entanglement. That's that's what I was saying. Yeah. Entanglement. That's everything that has to do gravity is entanglement. ER equals EPR. That's all that's being said with that. So if ER equals EPR emerges from a statistical model that was time stepped out, and those evolutional time neural net models and Wolfram are acceptable, they can be parameterized and optimized for anything you want to do, really. So what we need to do here is I wanted to get a good example of what happens when so let's yes I wanted to give a good example of what happens like a rotational operator. So back up. Um Sorry, I had to get the math thing out because this is what I named my state. So, the state psi, I want to do quantum operator Rx on psi. Maybe it'll let me do this. I may have to put it in. Yeah, hold on. This might do it though, and it might not let me do it. I but I want to demonstrate like what's even happening when you do a rotation on the block sphere at all. Uh, in a matrix representation, and I might show you like what it. See, I okay. So C naught operator. I wanted to do a rotational operator on something. So uh, ah, and a rotational X operator. So yeah, that's for real. Okay. Okay, so man, okay, so J. All right, so this is a rotational operator. I'm gonna show you now. Bare bones, just the XX before we rotated it. Really? Hmm. I wonder what happened there. I just had it like queued up and then it disappeared. No. All I did was copy it, like, and everything disappeared and I couldn't get it back. That does happen sometimes, so I very much already had this typed out. And then it do that. That was what we started with. And a rotational operator is this. So in the matrix linear algebra, it's rotating the x operator. So like the element association is a good designation. It creates a bunch of different sparse arrays, which is what it is built of, because it's not just like a state. It's made up of motion. So these can't be pinned down as just like a value. It had to be displayed as objects themselves. Breaks everything down into quantum objects. But this is mostly just a matrix, a sparse matrix that they've built dimension out to. Go back out to the documentation. Quantum circuits. So why are we even doing any of this? Why are quantum computers important? Why are we here? What are we doing? The claim is there are several algorithms that named algorithms that they claim give you a speed up. I I'm skeptical and have been about all of it, but I I wanted to work with it to see. The claim is that with every qubit that is entangled together in your circuit, you get an exponent amount of states that you can have for, but once you measure it, you're going to collapse that amount of states. So ways that they do things, they get around bits of that are, well, don't measure all of the gates at once. decompose your value a bit at a time. Collapse one of the gates, but continue entanglement. When you measure, you will lose entanglement. So keep that in mind. That's why when you see on these charts, once you see a gauge, you don't see any more characters on that same line down the line. That's not something that usually happens because you've already collapsed this gate, and mid circuit, you're not going to have time to reset uh, a gate you've just measured. And for one, to entangle it back to its origin state at the beginning anyway is a kind of a no-no. This is kind of already run. So once you pull entanglement from part of it, you do lose that amount of computation, I guess. But so that is the claim. You have more computational ability, and if you don't measure it all at once, you don't lose everything. You can claim some of that. So we still have this entangled state. We measured part of it, and then we measure another part of it, and we measure another part of it. So after three different circuits at three different times in the amplitude of this function, I guess, we can decompose because there's going to be a matrix representation, a block sphere representation on the other side of what's going on. Once you get the other side, you've run your circuit, you've done your measurements, you've collapsed all of the circuits. It's time to reset the circuit. So when you see a circuit, I don't know, if you ever see a circuit that's got measurements all willy-nilly, be weary of it. It's probably not, it's probably a practice circuit that somebody's just practicing where to put stuff. I mean, it might be a good thing to put in this package, maybe, when someone does try to put a measurement in a funny place. Or like they can put their measurement there, but then it should kill that line. It should kill that circuit line once they do. That should be uh, it's the formalism, I believe. So a root x and a controlled root x uh transpose and a controlled root x, and a controlled x and a controlled x. Um yeah, let's look at that. Let's unpack that. A super dense coding. I love this documentation for learning purposes. Like you can literally learn everything you need to know about quantum information theory through oh man, it's a small price to pay. Such a small price to pay for greatness. You don't have to write dagger. You can literally go to insert special characters and the dagger operators in there. I it may take a while to find it, but it's in there. And don't scream at the computer like I've looked through every page in here. It's not in there, I swear. It's not in the arrows. It's not in the it's Oh my God, no, I've been through everything. It's in there. I swear. You'll find the dagger uh operator that's just like how it shows here in the picture. You'll find that. Okay, so I I say I want I kind of want amplitudes for it. So we have every arrangement of bras and cats here that all converge to an amplitude of either 1 or 0. So because there's 3 qubits, this is how 64 probably. Uh, yeah, it's the length 64. That's what I'm saying about Wolfram being such a great computational tool. Look at all the stuff it's doing without. I'm just clicking buttons. You don't need to be trained in any way, shape, or form to operate this tool and look like you know what you're doing. Not to say that I don't know what I'm doing, but it makes me look like I do a lot better. You know what I'm doing, Buzz? Actually, just getting it just a couple of weeks ago. Only, only a couple of weeks with this program. That's so cool that it will do that. Okay, okay. It's nice. Super dense. How to mods and switches. Um, Quantum teleportation. I like that. I like that. Quantum phases. Oh, so we have Grover. We have Grovers here. Do I need? Is that something saved? F is something saved though. I'm gonna run through this. Why no? Okay, I'm sure it's fine. Oh, I should have. That's the multi-way. That's before I even get into this. I'm gonna go to the graph multi-way system. Also, I want to see if it will build. Um, for instance, sweet. Yeah, you can even turn them into quantum states. Now you see what I just did. I turned a graphical format of what I want, and what it is a. I'll show you in a moment. Uh, There we go. That's super cool. Oh my goodness. You can even make it into an operator. So I took, run this again so I could get the, like, this is a directed edge. Well, maybe, yeah, it's a directed edge graph with a bunch of nodes, which you can use in so many applications. It's a zero-dimensional hypergraph, which is how most of these quantum objects, that's what it is essentially. It's there. These are uh the elements in these matrices are essentially going to be nodes in a zero-dimensional hypergraph. And unless you direct them like this, it will just they won't have edges. But that's how the computer is thinking of. And that's kind of how computationally they end up being. We project them onto like a Riemannian manifold and do a Hamiltonian operator of time, and there's like a wave function that you obey, and it's pretty straightforward that using tensor calculus like this with nodes is actually just bloody brilliant. And the fact that you can just take a graphical picture of a node network like that and turn it into a quantum object or turn it into a quantum operator itself was just, oh my goodness. I was just curious of how you even do this. You can, sure. So the multi-way system, I wanted to go over here. Mm. So the quantum to multi-way systems, I just made it a weighted, no, I made a Kirchhoff matrix. Now I'm going to make a weighted adjacency matrix. Now I'm going to make incidence matrix. And just a normal, just that weights. And then I'm going to turn each of those into quantum objects, just to show that you can. I'm also going to turn this into a quantum object, just to show that you can. Ah, turn this into a quantum operator. Now this had a whole bunch of, you can see it above, there's a bunch of, I didn't quite like that maybe, so let's get rid of the circuit part. Just, there's a lot more going on. But yeah, I figured it'd be all over that because the graphical part. No, there we go. We got an output that time. Do I get the same thing if I wrap this? Yeah, I get the same thing. So And so there we go. Check this out. This is how the computer and maybe life thinks of the universe as a directed edges. The system finds that easy to converge uh, sets of basis state. You, at the end of the day, everything is kind of a quantizably small amount of energy if we choose to look at it that way. You shouldn't though, because we're all a wave function. We're all embedded in the same wave function. So the thing with the measurement uh problem, I we may be able to solve this with Wolfram. We may figure out why it is that when you go looking for a particle, there is one, but there isn't. There isn't particles, there's just waves. It's for all intents and purposes a wave function. And even when they are particles, it makes more sense for you to do the math as if though it was a wave anyway. So just call them waves. But if you want to get persnickety and say that there is a fundamentally small amount of energy packet that Planck says you can't escape. If you get smaller than this, the laws of physics just are they break down. They're completely unnecessary. There is a a number for that where just everything breaks down and Planck and Euler came up with these bounds. The computer, though, can take and evolve these systems of just nodes with weights, or not even weights, just designations, and grow systems over an evolution of time. This is a quantum to multi-way system. I- And uh, these are so important because so we have this. I made this into an operator. Let's look at its matrix form. Matrix form. So when I take this, you can see what's going on here. 2 degree. Mm, just too big. Became too large. I did a simpler version of things to come. So there it is. Jonathan Gerard. Gerard? Gerard? Incredibly impressive. Jonathan Gerard. And then I seen a video of who I think that is, and he was incredibly young. It was very impressive. He wrote all of this documentation and perhaps the language. Not the not the language, but I mean the packlet, quantum packlet. Props. Props to you. This is beautiful. All of it is beautiful. This looks like a Hamiltonian branch. Hamiltonian operator branch, like with the. Let's take that. Let's take that. Actually, let's look at the. Yes, screw. Or scratch. You know what? Just go over back to the. Page. Look at partial trace. Tensor product is a function that you can make. You can, but you don't even need to use that though necessarily, unless you like explicitly want that in like the decomposition of your information of the state. Quantum partial trace, returning back the basis. Once, so we had a state to begin with, and we made it larger, 2 qubits, 4-dimensional. And then there was this looks like a trace on 2 and 3. And it returns X and 2's names. Everything's so like intuitive. I alpha beta. See, I was I've tried this so many times and it's like error. I've always wondered why. Or it's things just like this. I've had trouble just making quantum states with amplitudes that I name like this. Okay, so with nothing else, if I go psi equals phi minus, which is a dumb thing to do because you can make psi equal psi, or you can make it phi minus like the you probably can even just write phi minus. It really didn't copy. Random unitary operators. Okay, yeah, so doing like, yeah. Should have been more prepared with what I should have picked to have ready to go. Like, the documentation is so rich, it's hard to pick which examples are best to use. They've done a lot. But power to math and science, I wanted to show you guys a different line of inquiry, though. So, like, hmm. What did we want to do with actually? It's calculus time. Here we go. So there's like operators over branchial space. Okay. It's like a Fourier style spider. Looks like maybe. It's got some X and Z spiders. It's a ZX calculus diagram. And these can all be used to explain state diagrams of most things. Yeah. All things are convertible into all of these things, and it's nothing is subject to constraint anymore. You can do literally everything with anything. Thank you guys for watching. I'm sure I've been a long time. Uh, I'll see you guys tomorrow in the next study group. Thank you for coming to the first live study group. I appreciate it. We'll see you guys at the next one. I'll answer all of the questions that I get in the emails. Thank you. You guys can comment. Anybody else who doesn't is unsure of what was going on. I spent a lot of time silent. I know that. I was just going around through the documentation, flitting around looking for something good. And I apologize for that. You should look around through the documentation if you're curious to learn things, because that's where you there's usually a lot of real world situations where like somebody had a homework problem or something type when they tell you what it is even not that there was a homework problem, but they tell you that what the constraints were that they were looking for before, and then what that looks like to type that out to Wolfram.